Hey class, we have just talked about current, voltage, power, resistance, and this video is going to venture into how to manage more complex circuits, specifically resistors that are in series and resistors that are in parallel, so more than one resistor. We have already covered, if we look at our Unit 5 objectives, kind of this basics of electricity, including basics of current, right, check, basics of battery voltage, the basics of resistance in a wire, and the basics of Ohm's law. All of this has been covered with the SL video presentations. But now we're going to actually be drawing, interpreting, calculating current and voltage in more complex circuits, such as series and parallel. We're also going to calculate the equivalent resistance for combinations of resistors in parallel and series circuit. That's our goal. In order to do that, we need to remind ourselves of some equations that we're going to use. When we look at 5.1 electric fields, we kind of covered a lot of this already, right? Like this and this, and so even some of this, it's all like older stuff, but it can become useful, specifically when we're talking about the definition of potential difference voltage, or like how a electric or electron feels a force inside of a wire, right? Because it feels an electric field. But mainly the new stuff we're working with is over on the right side, right? Because actually we've already covered current is the rate of change of charge, and current is dependent on some sort of drift velocity. And so we're going to look at Ohm's law, R equals V over I. We're going to look at this power equation, which can be extrapolated into two other equations. And then today we're going to look also on resistance in series and parallel, which they aren't explicit about, but one of these is for series and one of these is for parallel. And then, hey, we've already seen this before. This was back in resistivity with the video from previous. We're not looking at Kirchhoff's circuit laws. That's going to come next time. So we're just going to try to use these kind of base equations to understand how circuits work. Now, it's important to know why we're doing this, like where does this all come from? And it really comes from the concept that the electricity that we receive comes from power stations, right, which we've already learned about. It gets sent through these wires, and it gets distributed across residential, businesses, other forms, in this kind of more complex power grid. When you look outside, you see the electrical wires. That's a circuit. It's super macro though, so we're looking at the big scale. And we might zoom in and say, well, what about at our house? And like, what does our house look like? And our house might be also kind of complex, maybe even more complex, because there's just so much going on in our house. Like every single room has wiring through the walls to either go to your computers, your TVs, your lights, your switches. Everything has wiring going to it, and it has more, right? Everything's a resistor, so everything is involved in this circuit. So there's obviously more than one resistor in the circuit in pretty complex forms of this. So that's the reason why we have to like first start off with just like very basic versions of a circuit and kind of start there and then get more and more complex. So we have this circuit where we have this battery cell, and it has a potential difference, which I'm going to call like V tote, because it's like the total voltage, or the V battery, that is producing a current. In fact, though, this conventional current's going the wrong way. This should be going this way, and that's creating some current, and that's going to be passing eventually through this resistor, which I'll call this current I1 because I'm calling that resistor 1. Technically, we're going to learn that in series they're the same, but it's good to kind of not adjust our equations until we know for sure. So we've learned from the videos about potential difference, about Ohm's law, and so like the question is, what is the potential difference across the lamp? Well, I have it written here. My potential difference is equal to I1 times R1, and you notice that I'm keeping the subscripts in there. And that's going to be useful to kind of just be consistent and only adjust when we know things to be true, such as like the current. We might already know the current. We don't need to write I1. It might just be I. And what is the power dissipated by the lamp? And that is going to be, and I'm going to call it P1 is equal to I1 times V1. Again, focusing on recognizing that the power dissipated in the lamp is equal to the current times the voltage of that lamp. So in fact, it's not in V1. Maybe it'd be better if I wrote the potential difference across the lamp. That's a better way of writing it. All right, and these are always true. Always true. Series, parallel, doesn't matter. It's always true as long as we remember to keep the subscripts. We kind of get in trouble if we make adjustments without knowing for sure why we're doing that. So we have a 2-lamp circuit or a 3-lamp circuit, and these are resistors that are in series, meaning they're in line with each other. I might want to start identifying different variables in the circuit. So we would have a total voltage, we would have a total current, we would have resistor 1 and resistor 2. And if I want to be super specific, I might say, hey, you know what, there's a current coming through and it's passing through resistor 1, so I might call this current 1, and I might call this current 2. And we can stop. And the same thing goes, right? It would be some total voltage and then R1, R2, and R3, and this I tote. Now, we're going to look at the current and the voltage that occurs as we add more resistors in series to the circuit. So I want to go to a FET. And I've already built the circuits for a 1 resistor circuit, a 2 resistor in series, and a 3 resistor in series. I want to look at the brightness, which is going to refer to like the power emitted by the lamps. I want to look at the current, and we're going to eventually be able to look at the voltage using our voltmeter. So as we're looking through these circuits, we can see some significant differences as we move across. One, the brightness in the first to the second to the third is dropping quite a lot per lamp. So that means that the power emitted at each lamp is going to be split somehow. Power is related to energy conservation, so we want to bring that up. And also, the next thing we can observe that the FET is doing for us is these circuits, electrons are flowing a lot faster in the first one, slower in the second one, then even slower in the third one. And that makes sense when we add a resistor or we add more resistance to a circuit. It's going to decrease the flow of electrons as it kind of hinders the motion of the electrons. And we see that this is all a series circuit, meaning there's one loop in each of these. And that's important to remember as we're moving along this unit. So now let's actually take some measurements and say, okay, what actually happens in our current and our voltage? And so I've added a ammeter and I have a voltmeter that I can play around with. This is how you would connect the ammeter. The ammeter is connected in series, meaning it is in line with the circuit, where the voltmeter, and this is where we're going to talk about something in parallel, is not attached to the circuit. It's kind of like it's going to be connected to the circuit via what's called junctions. So if I were to like push this right here, that is creating a junction right here because I am creating a like an intersection or a split. So I'm going to first, find the voltage of our battery. It's 9 volts, which of course if I click the battery, it shows 9 volts, so that matches. And then I'm going to look at the voltage across each resistor. And I have 3 volts, 3 volts, and then 3 volts. You might also notice that if I were to switch these, I put like the red on this side and the black on this side, I would get negative 3 volts. That's just because potential difference does have a positive or a negative depending on which direction we're going. So, and you might think, oh, they all have the same voltage, but that's also because they all have the same resistance. So we're eventually going to play around with the idea of making different resistances in these. I'll make it 5, 10, and 15, which will be used later. And you'll notice that the current still stays constant throughout the circuit because it's one big loop. But now the voltage, this is 4.5. This is 3. And you might guess what this is. 4.5 plus 3 is 7.5. And so this is 1.5. And we know that we have 9 volts in total to provide. So we're seeing the voltage is distributed amongst the resistances depending on how strong the resistors are, 5, 10, and 15. So there is a proportionality between voltage and resistance, which is our Ohm's law relationship. So in each resistor, what do you notice is that current stays constant. And that this is like our number one. We need to remember this. In a series circuit, we have current that stays constant, and voltage is distributed among resistors. So this current stays constant means like I1 is equal to I2 is equal to I3, which is equal to like I total. And so that's something I want to refer to later when we start kind of playing with the math. The voltage that's distributed among the resistors means this V total is equal to the potential difference across the first resistor plus the potential difference across the second resistor plus the potential difference across the third resistor, if there are three resistors, right? If there's just two, it's just 1 and 2. And how is energy conserved in the circuit? Well, we know that the initial energy is equal to the final energy. We know the voltage is kind of a form of energy, right? It's like an energy density, joules per coulomb. So we can also think that this total power is going to be equal to the P1 plus P2 plus P3. As it moves around the circuit, it's kind of dropping off energy in each case. We've also learned in class that this P total is equal to I total times like the V total of a circuit. And we've also learned that P1, and we just did this above, is equal to the I1 times V1, right? The current times the voltage. Oh, I should use a potential difference. And this is I2 times delta V2, and this is I3 times delta V3. Now, we said that I1 is equal to I2 is equal to I3 is equal to I total. So actually, these are all just I's, and I'm going to cancel them out. And I end up with, hey, something we just wrote that we observed, which makes sense, is V1 is equal to, V total is equal to V1 plus V2 plus V3. That just means that the total potential difference available by the battery is distributed amongst the resistances. So each resistor gets a voltage. And then we also said, hey, how much did that voltage matter? From above, we said, hey, this is equal to IN times RN. But IN is constant. I1, I2, I3 is equal to I. So let's plug this in, though, and say, okay, I times R total, because it's V total, right? So we're just switching out N with total, and we know that current stays constant, is equal to I1 times R1 plus, we don't need a 1 on that I, that's just an I, because it's the same, I times R2 plus I times R3. And again, we can cancel out the I's, and we get this important R total is equal to R1 plus R2 plus R3. Meaning, as you add more resistors in series, the total resistance of the circuit increases. It's a kind of an increased relationship. So what we're really doing is, what does this R total mean? Is we're taking this circuit and we're saying, you know what? I want to create an equivalent circuit where we're only thinking of like, and this is like our resistor, where instead of having 3 lamps, we're combining them and just saying, what is my resistance if I were just to not make it complex with 3 lamps and just say if there's 1 total resistance. And this is called an equivalent resistance. That's what this is. So you might see R total, and you might also see REQ. That's the same thing. So the only thing that changes in the circuit is this REQ. And I want to reference where this REQ is observed. It's actually R total there. Yeah. You'll see it in IB problems, so it's just good to remember. But our data booklet says R total, like I'm doing. Okay. So I want to play around some more. I want to create a circuit with a 5, 10, and 15 ohm resistor. I want a 10 volt battery, and I want to find the potential difference across each resistor, the current at each point, the power dissipated at each resistor, and the total of power available by the battery. I'm trying to kind of just make sense of the numbers completely. So the good news is I already have a 5, 10, and 15 ohm circuit that I just created. I have not made the battery 10 volts, so let's make it 10 volts. And what I'm going to do is I already have the current passing through each, but I'm going to measure the voltage of each, like this. And I'm going to write them down, and then I'm going to calculate power and so forth and kind of look through the math of this. So I'm going to pause this, and I'm going to be able to finish my table, my resistance, current, and voltage table, and then we're going to talk through power. So I would like you to open up the FET circuit, which is going to be linked in the comments below, and do this on your own. Write the table with the 5, 10, and 15 ohm resistor. The battery is going to be 10 volts, and try to complete this as much as you can, and then come back and we'll check our numbers. So I'm going to give this like 5 seconds, and then I'm going to pause and put the numbers in. Okay, I've got my numbers in. I've changed this battery to, this should have said total. I found that my current's 0.33, and I've done my voltage. Now, it's really important to recognize a few things here, and I'm just going to kind of write them in and then erase them. And that is, when I multiply my R times my I, okay, my Rn times my In, that's going to give me my potential difference across each one. So if I multiply these two, I'll get that also. Oh, I should not have an ohm there. If I multiply my total resistance by my total current, I get my total voltage. So that's true, right? So that's always going to be there. I'm going to erase that though because I don't want to overcomplicate this. I also know that the addition of all my voltages will give me my total voltage. And then I want to find power, and I know I can find power by saying my current times my voltage is going to give me my power. So I'm going to multiply these to get my powers. So again, do this, and again, I'm going to give it a few seconds. I'm going to do the calculations, add it in, and then we'll check our work. All right, so I've multiplied the current passing through each resistor by the potential difference of each resistor to find the power dissipated, or the power used by that resistor. That would be the brightness. So my 5 ohm resistor would end up with 0.55 watts. My 10 ohm resistor would end up with 1.1 watts, and my 15 ohm resistor would end up with 1.65 watts. And that should correlate to the brightness of each bulb. This is a 5 ohm resistor, so it has much less brightness than the 15 ohm resistor, which confirms what we like. Again, I'm going to erase these multiplications because I don't want to overcomplicate this. But I also want to add in one more thing, and this is our power energy conservation rule. When we add all the powers dissipated by each resistors, we should end up with the power that's provided by the circuit, by the battery. Now, to cover some key takeaways, we're going to separate it into takeaways that we have always true for every circuit, and then what's true for a series circuit. So what's true for every circuit is that the total power is going to be distributed. That's always true. We also know that the power in a resistor is equal to the current times the potential difference across the resistor. And we also know that the potential difference across the resistor is equal to the current across that resistor times that resistor itself, with the focus on these ends, and this end can be replaced with total, right? So that also means that this can also kind of imply that the total voltage is equal to I tote times R tote, and same thing here. This can also mean that the total power is equal to I tote times the potential volt. So that can also mean that. Now, for a series circuit, our focus is on what happens to the current and the potential difference across each resistor, and that is where we get current stays constant across each resistor. And then voltage, or potential difference, is distributed. So it's not constant across each resistor. All right, so that sums up a series circuit. It's really important to know those key takeaways. That's always true. We're going to revisit those, and then the key takeaways that's specific to a series circuit. And that's it for series. Next video I'm going to make is going to be on parallel. So right now it'd be good to either take a break and complete the series practice, or move on to the parallel if you want to just you want to just take all the notes.